Welcome back, everyone. Let's just dive right into this explainer, because today we're on a mission to settle a massive, literally universe-spanning cosmic mix-up. And you know what the funniest part is? It's a mix-up that happens almost every single day, right in our very own bathrooms. We throw around two highly specific scientific words interchangeably, completely ignoring the fact that they represent entirely different concepts in physics. I'm talking about the ultimate intergalactic identity crisis: mass versus weight. By the end of our time together, I promise, you are never going to look at a bathroom scale the same way again.
So think about this. Why do astronauts bounce on the moon? We've all seen that iconic footage, right? Taking those long, slow-motion bounding leaps across the lunar surface. But here's the crucial point to remember. They didn't go on some crazy crash diet on the rocket ride over. They kept the exact same physical body, the exact same amount of physical matter, but they're suddenly experiencing a completely different invisible force. So their bodies haven't changed at all, but their environment's pull on them absolutely has.
Which brings us to Section 1, the everyday cosmic mix-up.
You see, when you step onto a scale in the morning, you probably think to yourself, I'm weighing myself. But scientifically speaking, you are actually finding your mass. The term weight is constantly used in everyday life when mass is what we actually mean. In physics, these two ideas are entirely distinct, and they even use completely different units of measurement. But over time, we've blurred the lines so much that it's basically created this global linguistic blind spot.
A standard electronic top-hand balance perfectly illustrates the problem we're dealing with. It's this beautifully precise piece of scientific equipment, and we use it for a process that we unfortunately call weighing. But here is the great irony. That balance is actually designed to measure mass, not weight. It spits out a reading in grams or kilograms, right? And those are strictly units of mass. Honestly, it's a bit like looking at a thermometer, getting a reading in degrees, and then calling it your length. It just doesn't make sense. So if the scale is actually measuring mass, what exactly is mass?
Let's get into it in Section 2, Mass, your unchanging matter. By definition, mass is a measure of the quantity of matter in an object at rest relative to an observer. Now, to put that simply, it just represents the actual physical stuff you are made of. Your bones, your muscles, your atoms, the sheer quantity of your matter. And here is exactly why mass is the stubborn hero of our story. It's exactly the same whether you're sitting in your living room, floating around in the International Space Station, or standing on the surface of Mars. It literally does not care where you are in the universe. Your mass is your mass. And mass actually has this secret superpower: inertia. Inertia is defined as the property of mass that resists a change from its state of rest or motion. Basically, it means mass fundamentally hates change. If an object is resting, it wants to stay resting. If it's moving, it wants to just keep moving. The more mass an object has, the harder it is to push it to get it started, and the harder it is to stop it once it's finally rolling. This physical stubbornness, this resistance, is inertia. And it's a direct measurable result of how much mass, how much actual matter is sitting right there. Because mass is so incredibly fundamental to, well, everything, we need a standard way to measure it. And that standard unit is the kilogram. But get this, until very recently, the year 2019 actually, 1 kilogram was officially defined by a literal physical object. No joke. It was a highly protected piece of platinum iridium alloy just locked away in a vault at the Office of Weights and Measures in Paris. Literally every kilogram in the world was based on that one specific lump of metal. Now, today, scientists have finally updated it to rely on a precise fundamental physical constant, but the history there really just shows how incredibly seriously we take the measurement of our matter. Now, on the flip side, we have Section 3, weight, gravity's invisible pull. So while mass is our stubborn, unchanging hero, weight is more like a fickle, location-dependent sidekick. Weight is defined as a gravitational force on an object that has mass. I want you to notice the key word right there: force. Weight is not stuff. Weight is a pull. It's a vector quantity that represents the actual physical downward pull of a planet's gravity on your mass. You're constantly experiencing this on Earth, of course. It's the exact reason why an unsupported object drops straight from your hand to the ground. And honestly, this brilliantly illustrates just how strange gravity really is when you stop to think about it. Weight is caused by gravity, and gravity is what we call an action at a distance force, meaning there doesn't need to be any physical contact at all for these forces to work. It's just like magnetic forces pulling two magnets together across a gap, or electric forces causing your socks to stick together with static cling. The gravitational force literally reaches out through empty space and just pulls on your mass.
We explain this invisible reaching force using the concept of a gravitational field. A gravitational field is simply a region in which a mass experiences force due to gravitational attraction. So, to put it together, your weight is simply the result of your mass sitting inside one of these gravitational fields. And here is a totally mind-blowing fact from our source material. Because the Earth is not a perfect sphere, it's actually kind of squished, a bit flatter at the poles, you are technically closer to the center of the Earth at the North Pole than you are at the equator, which means the gravitational field is actually stronger at the poles. So you literally weigh slightly more at the North Pole than you do on a warm beach at the equator, even though your actual mass hasn't changed by a single atom. How wild is that?
Now, because weight is a force, it really shouldn't be measured in kilograms at all. The scientifically correct unit of force, and therefore the correct unit of weight, is the Newton, represented by a capital N. To give you a tangible physical anchor for what 1 Newton actually feels like in the real world, just imagine holding an average-sized apple right in the palm of your hand. That subtle downward pull of gravity you feel from the apple, that is pretty much exactly 1 Newton of weight.
Okay, let's tie this all together in Section 4, calculating the universal difference. So, how do these two concepts actually relate to one another? Well, it all comes down to a beautifully simple equation straight out of Newton's second law of motion. W equals mg. Let's break that down. Here, weight, that's the W, is our force. Mass, the m, is our matter, and that little g represents the gravitational field strength. Down here on Earth, g is about 9.8 newtons per kilogram. So, if you want to translate your mass into your weight, all you have to do is multiply your mass by the strength of the gravity field you just so happen to be standing in. Let's actually see this cosmic math in action. Imagine we have a 100-kilogram astronaut. Remember, their mass, that 100 kilogram, is their physical stuff, their inertia. It stays exactly identical no matter where they travel in the solar system. But just look at what happens to their weight. On Earth, with a gravitational field strength of 9.8 newtons per kilogram, they weigh 980 newtons. Now, if they take a trip over to Venus, gravity is slightly weaker there, so their weight drops to 880 newtons. Head over to Mars, gravity is much weaker there at just 3.7 newtons per kilogram, bringing their weight all the way down to 370 newtons. And on the Moon, the field strength is a measly 1.6 newtons per kilogram, so their weight absolutely plummets to just 160 newtons. And hey, this is exactly why they bound across the lunar surface. Their leg muscles are completely used to pushing against 980 newtons of force all day, every day. But suddenly, they only have to push against 160. It's like having instant superpowers. Which brings us to one final, completely fascinating thought experiment straight from the explainer source material. Imagine our astronaut is on a journey back to Earth. Along the way, they reach a very specific, unique point in deep space. Let's just call it point X, where the gravitational pull of the Earth and the gravitational pull of the Moon are perfectly equal in magnitude, but completely opposite in direction. Basically, they completely cancel each other out. The resulting gravitational field strength at that exact spot, it's 0. So if you multiply their 100-kilogram mass by a gravity of 0, their weight is 0 newtons. They are entirely, literally weightless. But, and here is the truly beautiful reality of physics, they still have a mass of 100 kilograms. If they try to push off a wall inside their spaceship, they're still going to feel that exact same heavy, stubborn inertia resisting them, because mass is forever. So the very next time you step on a bathroom scale, ask yourself, are you really worried about gravity's invisible pull, or are you just checking in on your unchanging matter?